Got the supercapacitors mostly put together. We had a few of them that came with electrolyte that was leaking out of the rim on top. So I ordered a new set, but they didn't have any more of the 2-foot ones available, so I got a 4-foot. I just put the feet flat down so that my little balance boards could fit up on top of there still. So they'll still sit on there. We'll get to attach those. I'll just fill those holes with solder. As it turns out, when they're standing upright, they're spaced out further than the 2-foot ones are, so this won't go over the top of it. So I had to flatten them out. So those last 3 will be 4-foot ones. They'll go right there on the edge. Once it's all put together, they'll lay flat down. I bought these components. Each supercapacitor is $2 each off AliExpress. These balance boards are like $1 each. So this is $3 per. You only need to have the number that you required for your voltage. So because we have a higher voltage, you need to be up to 117. You just take 2.7. Well, you take your voltage divided by 2.7 and you see how many you need in series. If you did a 72 volt system, you wouldn't need this many. You would just need, whatever that is, 87 volts divided by 2.7, you get your number. The bus bars are just copper bus bars. I bought 3 1/3 meter length each. It was like $10 for the bus bars. Pretty good, price honestly for what you're getting out of it. And I just soldered the wells completely full, so everything's touching. Each of these, I have some burnt ones. I'll show you. They come with a metal ring, and so it's actually able to transfer energy through there pretty quickly. So the bus bar is flat against that, which is contacting the pin that comes out of the capacitor. And so everything's contacting, the solder is just there holding it together. But I wanted to make sure there was as much conductivity as possible, so I just filled it up with solder the whole way. I didn't want there to be anything that was like heating up or becoming a fuse in the pack. I wanted it to just be able to provide what it needed through the cables. So it's actually pretty simple. I mean, you just run them in series, and then obviously I had to jump from one end to the other, and then it's a lot like a battery, how you connect it. And this just wires up in parallel with the batteries. So I'll put a Anderson connector, I have some there already, and it'll just be positive and negative. We'll plug positive and negative in, and that connects to the positive and negative of the battery. It's pretty simple. It's just not used very often because it's not energy dense, meaning you don't have a lot of storage for the amount of space or weight that it takes. And these are actually surprisingly light for how much volume they take. Compared to a battery, this much of battery would probably weigh like 20 pounds. This is only 7 pounds, 7.5 pounds, and it was 7 pounds, 8 ounces, 9 ounces, something like that. So quite light, and we have a nice spot for it. It's gonna go on the bottom as a skid plate underneath the batteries and the motor. So you'll kind of not even know that it's there. It'll just be like a wire coming up the back.
Yeah, it's gonna look good.
Pretty sweet. It won't have much weight, and it holds, I think it holds 0.03 kilowatt hours. If you were to calculate it out with, making it battery terminology, they don't measure it in kilowatt hours. It's all measured in farads and units of charge, not units of capacitance, which measures charge, not units of energy. But if you were to convert it, it's like 0.03 kilowatt hours. So small. A battery this big would hold a lot more than that. That's just 30 watt hours. So it can provide 30 watts for 1 hour. Not a lot of energy there, but it'll be enough to get some motion. We'll see how far it actually takes. But the main purpose isn't energy storage, it's energy repository, right? So it's as it comes in and goes out, it comes in and goes out either direction. It can sit here, keep this full. This can provide excess power. It can store excess power instantaneously, not long term. That's the intention. There's a lot of things that got us to this point. I'll give you the full backstory. So a lot of you noticed and knew that when we put the throttle on, it would cut out. And there was no setting I could change that would fix the problem, but there was a couple of moments of light when I switched the pulse width modulation. Basically what happens is when the motor's at a low speed, it's taking full voltage of the battery pack, but it's converting it to a lower voltage so that it can start spinning more smoothly on the bottom end. And so what'll happen is the controller will actually take pulses of electricity instead of a full. It won't just keep a constant current coming. It'll take a pulse, 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 pulse along a modulation of the sine wave, right? And so when the pulse was super narrow, it would be asking for a ton of current in a small window of time, and it couldn't handle it with the battery that we had. And so what would happen is I switched the pulse width modulation to 20 instead of 10. The setting is really like 20,000. And what happened is the bike just took off for a second. And so I realized that the problem is it's asking too much current instantaneously during the pulses. So the solution to that is a supercapacitor, and we were the first ones to actually make one, document it, test it, and show it to anybody. There was one company that made one that put on a bike apparently, but no one ever saw it work. So this one actually is 500 farad individual capacitors, which we're running them in series, and so the farads drops as you run them. So between the 44 we have, what we get is 11 point something farads. What a farad is you get 11 amps given for 1 second to drop the voltage by 1 volt. So it's not actually holding less capacity by running it in series, it's just the voltage doubled, and so the amount of current required is cut in half to make it drop a volt. So it's the same capacitance in 1 as there is in 44. We just needed to do that many in series because they're only rated for 2.7 volts each, and if you put 1 on there and charge it to 117 volts, it would fry. So in order to get to 117 volts, I needed 44 of them. So the voltage can handle it, and we have a fairly large capacitance still out of that. We're going to do some tests where we can see what just the supercapacitor does. So we'll have it, so just the supercapacitor is running, how far can the bike go, how fast can it accelerate, so all of that. What we're doing today, before we close it off, is kind of testing it out. So I have it charged up to, well, okay, let me tell you what the capacitor is going to do in case I didn't get there. The supercapacitor, or any capacitor in general, can charge and discharge almost instantaneously. So when the battery can't provide all the current that the motor controller is asking for in those instances of the pulses, the supercapacitor can fill those in, and the battery can recharge the capacitor in the windows between the pulses, right? So battery and capacitor for the pulse, battery recharges capacitor, pulse, charge, right? So it's kind of alternating back and forth, so this fills in that gap. So now we're kind of, before we encase it off, we're gonna just try to make sure that it works correctly. I've got it charged up to like 103 volts right now. 103.6 volts on the capacitor, and it goes up to 117, but what happens is each of these capacitors has a balance board on top of it. You can see those here. It'll bypass the capacitor once it gets over 2.7 volts to keep the whole capacitor bank safe. So I'm going to turn the charger on and we'll see these things pop on. So this is just the bike's charger. I've got it wired in on the ends here, just taped up. So you'll start to see these lights. There's one light that came on here, so this one's balancing. You can see that light there. These ones are all at 2.7, so they're balancing out. Got a couple back here that are balancing. And it shuts off the charge to that capacitor and it just charges the rest of them at that point. So now it's reached 116 point something. Let's see. 117.2. So now these are not being charged, they're actually discharging. You can see the lights will turn off once it balances out between, it's going to push that energy off onto the others. So ultimately, once they all get to the right voltage, they're going to discharge at the same rate. But if there was an instance where one overcharged, it would just be able to bypass that. The rest of them have all shut off, meaning they're balanced out correctly. What will happen is as the energy flows through, it's just one electron moving between all of them. So it's not like one's going to get more than the other. Once they're all balanced, they're going to stay fairly balanced at that charge point. And then this one turned back on as it got recharged by another. So interesting that it's just kind of keeping it all in balance. Inside of the case though, we don't have to worry about it. This one's getting charged up again as well. They're kind of just all leveling out. Pretty cool the way that it works. It's being kept at, because it's still plugged into the charger, so it's technically still receiving some charge. It'll be kept at that voltage that it was at, so it's at 117.2 to 117.3 right now. So part of that lights coming on, lights coming off is it's still hooked up to the charger. If we unplug that, they would all stay off pretty much. So we haven't tested how much current it can output yet. I was playing with it and I burned a lot of wires just like seeing what it could do, and I calculated out how much energy it would carry, and in the usable voltage range, which is 117 to 82, the controller will shut off at, in that range it can provide 300 amps solid for a whole second. It's never going to need to do that it could provide, so 300 amps for a whole second would be, I mean, roughly, if you were to use the nominal voltage, that's basically 30,000 watts. So it's 30,000 watts just for this, from this for a whole second. That's all a capacitor needs to do. It'll be recharged between pulses by the battery. That's the intention of it. As you're regenerating from braking, it'll go into the supercapacitor as well. So it's gonna be just like a storage reservoir where energy can come in and go out of without having to ask a lot of the battery. The battery just kind of keeps it full. And obviously they're all working together. There's 2 batteries and 1 supercapacitor. That's 3 things that'll all be discharging and charging together, but this is a much faster charge and discharge, so it's easier to keep it topped off at the right voltage. So we're gonna see what it can do. I've got an amp meter that can clamp around it. I had it at 50 volts, and at 50 volts it wasn't even close to full. And in the split second of discharge, the one reading I got it to show was like 250 amps. But it takes a second for it to register, and capacitors discharge so fast that we probably just missed the very high peak of it, and then we caught the very tail end of it. So we're gonna try to see if we can get a discharge reading. I'm gonna get like something super resistive. I was thinking this like cable tie stuff, a tie down like a strap for construction, which is steel and super high resistance. So it should slow down enough to get a reading of what it can put out without just like blowing up, because copper just like explodes. So I bursted a ton of wires. So I also want to make sure that I want to make sure it's got less ability to run current than this. I don't want these to be the fuse, the cables, right? So I want something else to be the fuse. So we'll try this and see what we can do. I'll put the clamp on it. I'm gonna do it on the floor. You can see I have some sparks here from when it was popping with the wires. They're really easy to wipe off. We burnt the table though.
Yeah, we did.
Yesterday we were playing with it. And it just boom, and so it puts out a lot of power. So we're gonna see what it can do. All right, I'm gonna put some weight down on this so these don't jump. We're gonna see what this does. Woo-hoo-hoo! All right, we're gonna try that again. It's welded on there. We're just destroying this wiring. Totally worth it though. I'm gonna switch which one I'm attached to. Weld it on here now though, hang on. It was 116 when we started, and now that's down to 98. Welded and short circuit now. Nice. So all the power, that one I got in there fast enough that it didn't weld, it didn't spark, but you could actually hear.
Wow, that's crazy.
Yeah, we'll have to cut that off later.
Yeah. Warm at all?
Not noticeably. I mean, I feel like maybe, but it just put a lot of power through it.
Right.
Let's see what voltage it's at.
Feels room temperature.
I felt like electro boom for a while. Yep, 24 volts. At this point, it's effectively depleted, and there's not enough voltage to shock anybody. But if you were to touch this before, you get all that current through you. Second battery pack, discharge and charge, I guess it's going through here both. It's going to connect to the main pack in parallel through this. When this is plugged in, it connects to here, which then connects to here. So we connected in parallel through this. The voltages are about 104 and 105, so we're really close. I'm just going to plug this in first and this in to get those balancing overall. And then these cables from the main pack and from the secondary pack, which is here, connect each individual cell pairing in parallel as well. So we'll let the whole pack level off first by plugging those in, and I'll plug this in, and we'll get the whole thing, each individual cells, paralleled and balanced as well. packs are in parallel right now. Let that balance for a second. Nice. So each of those is connected properly in parallel with the cell that it corresponds to between the two packs. So these two batteries are now completely lined. The bike is charged up live.
But here it is. So you guys can see it. I mean, it sticks out just barely, which I don't mind at all.
I think it looks kind of cool. It's like a little propane.
Yeah, I agree. It looks kind of cool. And that way you can see it. I mean, it's such a unique thing, you know? You kind of want to be able to see a little bit of it.
You wouldn't know that it's there.
Right.
Like if you looked at this bike, you'd be like, oh cool, I see the battery.
Yeah.
Oh, what's that little skid plate on the bottom?
Yeah, exactly. Oh, you know, that's just a one-of-a-kind supercapacitor there. And you were still making room for the center stand, right? That's why.
Yeah, so I had to put it just enough forward.
It can get. Right.
It'll run through here, and then the cord should be out of the way enough that it can just go straight down from that point.
Yep.
Worst case, the supercapacitor is 3 bolts. So if you gotta take it off, you gotta take it off. But at least you can. It'll be attached for sure if you wanted to have it attached. But it might not be able to go down.
Gotcha.
We haven't tried it with it in, but yeah, you can see that the bars open there.
Yeah. No, it looks great. But anyway, supercapacitor is installed, and the drivetrain is 100% installed, right?
Yeah.
Look at that, dude. Goodness gracious. Freak, dude.